For me, it is fine, Alan. You can record.
Okay, thanks. I think it has to be done on the Maynooth side. So if Nick is online, I think Nick arranged it last time. Sorry, go ahead. Yeah.
Okay, so good afternoon, everybody.
Vincenzo, you're muted. Vincenzo, you're muted. Vincenzo, you're...
Yes, sorry. So good afternoon, everybody, and thank you to Professor Pallonetto for the introduction. As he mentioned, we are going to talk about the analysis of carbon emissions in the European Union, but the analysis will be developed by using two frameworks, which are the decomposition analysis and the decoupling analysis. So we will go through these two concepts, and then I will show an application of how they are applied to the analysis of carbon emissions in the European Union. The talk will take about 30 minutes, and then we have some 10-15 minutes discussion.
Vincenzo, you're on mute.
Okay, somebody muted me. Okay, so first of all, let me briefly introduce myself. I am a mechanical engineer, and I developed my career partly in the private sectors in industry and part in the university. So most of my academic career was developed at the University of Genoa, which is a partner of STREACS project. And since last January 2023, I am at the University of Naples.
We can't hear you.
Yeah, no. Can you hear me now? Because I don't know, when I press enter, I got muted. I found it right now. So just a very few words on the University of Naples Partenope. It is a 100-year-old institution. It's a very specific and quite iconic in the city, even though it's not the largest university in the city. It's very specific because all the disciplines or the study courses developed at this university have a direct link with the sea. So it's a university whose broad scope is focused on the sea and all the activities that are developed on the sea. So I don't know, navigation, economy, transportation, engineering, all with an eye devoted to the sea. So given this quick introduction, let's go through the agenda of the presentation. So first of all, I will introduce what is the index decomposition analysis. Then we mention the Kaya identity. Then we discuss the concept of the decoupling analysis, and we will have a look to the Tapio methodology for the decoupling assessment. Then I would illustrate a case study related to European Union. And finally, we jump to the conclusions. So, why it is important to analyze the carbon emission trend? Because according to the European Union target, we need, as European Union countries, to reduce carbon emissions. Why we need to reduce carbon emissions? Because they are highlighted as to be responsible for the greenhouse gas effect, and then for the climate change that is a consequence of the greenhouse gas effect. And so we need to analyze which is the trajectory we are following in reducing the carbon emissions. If this reduction has economic implications, especially negative economic implications, and if what provokes the reduction of or increase of the emission, which are the drivers for that, and we may want to assess if the policies, the actions that are put in place at country level or at the European Union level are having the expected impact on the emission reduction. So a common framework that can be used is the index decomposition analysis, IDA, that you can find in the literature. This framework is quite straightforward, and it helps us to highlight which are the contributing factors, for example, to the carbon emission. But this concept can be applied to other quantity, like, I don't know, energy consumption, tourism flow, whatever you want, other kind of emissions, because we are now talking about the carbon emissions. But you can apply to pollutant emissions like NOx, SOx, etc. So the framework is general. And the important thing here is that we are able, through this framework, to highlight which is the contribution of each parameters. And because of this, this value added, this approach is widely used in energy economics, environmental economics, policymaking, energy system analysis, and so on, because it is a simple tool that allows us to decompose complex phenomena in a chain of indexes. The most famous decomposition methodologies are two: the Laspeyres index decomposition and the logarithmic mean division index. From the mathematical point of view, both of them are relatively simple, but the Laspeyres methodology has a main challenge. That is that the decomposition is not perfect. So you are not able to decompose in a perfect way the different contributions, and there will be a residual. Then if you go through the literature, you will find that there are many techniques that are proposed to redistribute these residuals. And these techniques are not necessarily very simple, and sometimes they are very complicated and cannot be applied in general, but they are case dependent and so on. All this is overcome by the LMDI approach proposed by Professor Ang. You can find a lot of papers dealing with LMDI that gain a very relevant success because it's a straightforward from the mathematical point of view, and it is very accurate because you don't have residuals through this methodology, and so you can distribute perfectly the quantity through this approach. So you can decompose, for example, carbon emission in a perfect way. Then let's now introduce the Kaya identity. What is Kaya identity? It's a mathematical expression to define carbon emission. It was developed by Professor Kaya, that was a member of the IPCC panel. And this expression that we are going to see in a moment gained a lot of popularity for its simplicity, but also for its effectiveness, because it allows to explain which are the drivers provoking CO2 emissions. The expression is the following. Let's start from the down part of the slide. First of all, you can notice that it is an identity, because you can simplify population and population, GDP and GDP, energy and energy, and so you get CO2. So you get total CO2 emissions equal total CO2 emissions. So by introducing this product of 4 indexes, we have not altered the quantity, the expression, because you can see that everything can be simplified. So how Kaya developed this expression? So Kaya imagined that the total carbon emissions can be considered, can be estimated as the product of the population multiplied by the CO2 emissions per person. Then he went ahead and he said, yes, but CO2 emissions per person can be estimated as the results of the income times the technology. As a proxy of the income, he proposed to use the GDP per capita. It's commonly done in economics, and the GDP per capita can be seen as a proxy of the average income of the population. How to define technology? So technology can be defined as the product of energy intensity times carbon intensity. So energy intensity is a measure of how much energy is consumed per each unit of money produced. And the carbon intensity is the emission rate per unit of energy consumed. Why these two quantities represent the technology? Because from one side we have the the energy intensity can be a measure of how energy intensive is the economy, so how much energy you need to drive your economy. And according to previous paradigm, and in the following we are going more in depth to this concept, economic development and energy consumption increase with the same pace, because without energy you cannot have economic development. Then from the other side, the carbon intensity illustrates how clean are the technologies we are using to generate energy. Okay. So the multiplication of these 4 indexes gives us the total CO2 emissions, and we can analyze which factor has a greater impact. But to perform a better analysis, this multiplication can be transformed in an addition through, for example, by the LMDI methodology. And so the total CO2 emission can be explained in terms of how much carbon emissions are due to the increase or decrease of population, how much carbon emissions are due to the increase or decrease of GDP per capita, and so on. And so you can analyze the variation of CO2 emissions between 2 periods of time of your choice, as we see later on. This is very relevant because it's a very simple tool, but very effective. Limited benefits. We have a clear identification of which are the drivers. We have identified 4 drivers in a clear way. We can quantify the impact of each factor. So it's a quantitative measure. It's not a qualitative indication. It's very quantitative. And with these, for example, if in a certain period of time, some specific policies are implemented, we can evaluate quantitatively the impact of those policies. Also, we can use this approach to compare different countries. usually different countries in the same area with, I mean, countries that are comparable. For example, in general, we cannot compare, I don't know, Italy with China, because the dimensions are completely different. Dimensions of the country, dimensions in terms of population, in terms of magnitude of emissions, and so on. But you can compare Italy with France, Spain, UK, Germany, and so on. So in the same, among homogeneous group of countries. Which are the limitations? First of all, data availability and accuracy. I mean, you need the data to develop this analysis. Let me say that for European countries, this is not a problem because you can find plenty of data in Eurostat. There are extensive databases covering all over the world, for example, World Bank databases. And here it would be interesting to check, for example, which data are available in Armenia. I think that are available these data in order to make the exercise on Armenia, since it is scarcely represented in the literature. So this could be good. Then there is the complexity in identifying which are the factors provoking, for example, the carbon emissions, because what, for example, Kaya stated is a general equation. Then we may find that it is not true for whatever country you choose, but it can be applied just to some countries. So the application can be complicated, and later on I show you a specific example on that. Then, speaking about the Kaya identity, it is limited because we only capture 4 factors, but the factors determining carbon emissions can be much more. Decoupling analysis. What is decoupling? It's a very relevant and up-to-date concept, especially in countries that are front-runner in reducing carbon emissions. Because decoupling, as you can see in the first sentence, refers to the ability of an economy to grow without corresponding increases in environmental pressure. The environmental pressure is usually measured as the increase in carbon emissions. So when we talk about decoupling, we talk about the increase of economy with respect to the increase of carbon emissions. You have the decoupling, the absolute decoupling, if you have an increase of the economic parameters, for example, GDP, and a decrease of carbon emissions. So this means you are decoupling the economic development from the emissions, because you can grow, your country can grow, but decreasing carbon emissions. Then there is the relative decoupling, that is, your country is growing, carbon emissions are growing, but less than the economy. So your economy, I mean, the ratio is not 1-to-1, let's say, but you have a lower increase of emissions with respect to the increase in GDP. So energy, so example of methodologies to achieve the decoupling are the implementation of energy efficiency measures, technological innovations, but also the implementation of specific policies can support the decoupling. Now, we can quickly highlight a very simple methodology to assess the decoupling, that is the Tapio methodology. So, Tapio methodologies can be simply based on the ratio between the variation of carbon emissions divided by the variation in GDP. And according to this ratio, Tapio identified the 8 decoupling status. As you can see here, strong decoupling, weak decoupling, expansive decoupling, expansive negative decoupling, and so on, according to the value of delta V and delta W and the value of T, different decoupling status can be highlighted. Clearly, the main target would be the strong decoupling, where you have an increase of the economic parameters and a decrease of carbon emissions. What is very worrying for policymakers is the recessive decoupling. That means you reduce carbon emissions, but also the economic growth reduces. So you achieve a saving in carbon emissions, but also you provoke a compression, let me say, of the economy. And this is obviously not the main wish of the policymakers. Now, having said this, having introduced more or less some concept, but I invite you to consult the given references to gain a better understanding of the topic, we can analyze a case study on European Union that I developed together with some colleagues. This work is published on journal, you can see here, Science of the Total Environment. So you can find the details of the paper here. The paper is open access, so you can get it for free. So we extended basically chi identity because we used a 7 factors decomposition. So we introduced 3 more factors to analyze the carbon emission trend in the European Union. These are the 7 factors. We used the carbon intensity of the energy sector, and this is, you can find this factor also in chi identity. Then we used the energy structure of the energy sector, that is the ratio between fossil fuel energy consumption and the total energy consumption. Because nowadays in European Union, the contribution of the renewables is relevant, cannot be neglected. And so it's not enough just to represent the energy consumption through the, to represent the energy sector, let me say, through the energy intensity and through the carbon intensity. But we also need to understand how the structure of the energy sector is evolving. Then we have the climatic factor that also cannot be neglected today, because we know from the analysis of the historical series of temperature that temperatures are changing. So we need to understand how much the climate effect is impacting carbon emissions. The impact can be also, positive, can also lead to a decrease of carbon emissions. Because, for example, if you have a warmer winter, you will lose less fuel in the heating system, and this determines a reduction of the CO2 emission. Then we can debate if this phenomenon is positive or negative, but it is a matter of fact, and we can quantify this, that higher temperature in winter can reduce carbon emissions. In summer, instead, we can observe an increase of carbon emissions because we use air conditioning more. Then we have the energy intensity, as we have with chi identity. GDP per capita is the same as the chi identity. Then here we have the population share. That is the share of a population within the country we are analyzing under the region. So since here we have the analysis is focused on the European Union, here we consider the share that the specific European country that is considered, for example, Italy. So we have the ratio of Italian population with respect to the European population. And these parameters is a kind of a weighting parameters, and it tells us how much each country grow with respect to the total. And then we have the evolution of population in EU 27 countries. So all the effect of all these parameters is considered. Here you can see the full equation, the 7 indexes that are considered. And once again, we can prove that it is an identity because fossil and fossil can be simplified, energy and energy weather adjusted and energy weather adjusted. So this is the climatic coefficient, which is the ratio between the raw energy consumption divided the weather adjusted energy consumption. The weather adjusted energy consumption is an estimation of the energy consumption in normalized climatic condition. Okay? You can find in the reference the methodology. It's simple. It's based on degree days to determine this weather-adjusted energy consumption. This is GDP. This is the energy intensity, GDP per capita, population share, and total population. You can see that the parameters can be simplified, and you have CO2 emissions equal to CO2 emissions. So again, you have an identity. So this decomposition in 7 indexes does not affect the the second member of the equation. The identity is satisfied. Then we can change, we can move from here to here, so to the variation of CO2 by applying the LMDI methodology. And here you can see the application, the joint application of Tapio decoupling and decomposition, because this is the Tapio coefficient epsilon, but since we decomposed the CO2 emissions in a set of indicators, of a set of parameters, once that we can transform them in an addition, we can have the impact of each parameters on the decoupling. So we can get more information. So here I'm showing you which are the data at European Union level. So you have the trend in carbon emissions, and you can immediately observe that it is a decreasing trend. Population is increasing, and also the GDP is increasing. Let me say that to make this analysis, this kind of analysis, you need to use the GDP expressed in real values, because we compare, we make operations, okay, on mathematical operations on GDP values in different period of time. So here, data from 1995 up to 2019 are considered. So we cannot use, we need to use a real value. We cannot use the value, the money expressed in nominal value, because we would make a bad mistake, okay? Because money has a time value. Here you have the energy consumption, the RES share in percentage, and the transformation of the consumption in weather-adjusted consumption. So it's a representation of the main parameters that are used in the analysis. So here I reported this table because I was asked in the paper why you consider in the climatic as a climatic parameter just the heating degree days and not the cooling degree days. Because the heating degree days are a measure of the how cold is a country. Cooling degree days are a measure of how much hot is a country. And to answer this question, I calculated the linear correlation coefficient. And you can see that the correlation index between energy consumption and heating degree days is higher in average of the correlation coefficients of energy consumption and cooling degree days. That's why cooling degree days are not considered in the climatic coefficient. But this is for now, and this is for the period of analysis considered. In future, it can be higher, but also if we change the focus of the analysis, and for example, we switch, we restrict the scope of analysis, and we want to analyze, for example, electricity consumption, I cannot exclude that the relationship with the CDD is much stronger, and so we need to consider the CDDs, or in the weather adjusting coefficient, should be calculated by using the CDDs and not the HDDs. Even though, let me say that from the engineering point of view, there is some criticism on the cooling degree days. I mean, they don't work so well. But however, these are standard measures that are internationally acknowledged. Then, this is the results. So we analyzed the carbon emissions between these 2 years, 1995 and 2019. So, these are the 7 indexes I illustrated before, and this is the contribution that each index is given to the variation of the carbon emissions. So you have that the carbon intensity contributed to the reduction of 346 megaton of CO2. The energy structure to a similar quantity is 342, while the energy intensity contributed much more because it gives a negative contribution of 1,000 megaton of carbon emissions. And these are factors that depends on the technical aspects of the energy sector and the productive sector. That's why I named them technical factor. Then the climatic factor had again a negative impact of 362 megaton of carbon emissions. Instead, non-technical factors had a positive contribution to the carbon emissions, so basically determined an increase of carbon emissions. And the quantity that mostly contributed to the increase of carbon emission is the increase in GDP per capita, because you have more money to spend, or you make more money, let's say, and then to make this more money and to spend this more money, you consume more resources, and so you provoke more emissions. Then here you have the population share that measures how the variation, the variation of population between the different EU countries determined, had an impact on carbon emissions. It's negligible, it's very small. Instead, the increase of population determined an increase of carbon emissions of 143 megaton. So, between 1995 and 2019, you have a decrease in carbon emission from 3,340 up to 2,652. Which are the factors that determine this decrease and how much is the impact of each factors? So technical factors, climatic aspects, and non-technical factors gives you the quantitative answer to this question. You can see how much powerful is the methodology, because you can precisely assign the weight to each parameters. You can precisely determine the impact of each of these parameters. And then you know how to work on that. So this is very relevant. And immediately it follows the decoupling analysis, because we want to see if the increase in GDP is directly connected to the increase in carbon emissions. Because if this is not true, we have more space to act on technical factors and try to reduce carbon emissions more. So here you have the decoupling, the results of the decoupling analysis. You can see that I split in different sub-periods. So I didn't consider the whole period, but I wanted to be more precise and show the evolution. So we can see that basically in all the considered sub-period, there is a strong decoupling, and only in the period 2000-2004, there was weak decoupling. This is at the European Union level. For the different EU countries, and you will find it in the paper, the situation can change. So this is, what we have here. And so you can see how each parameters contributed to the decoupling, if positively or negatively. Because remember that here we were able to decompose the carbon emissions in 8 parameters, and then we can also split epsilon in the 8 contributions. And here in the chart, you can see the results of these 8 contributions. Okay, and so you can see which are the contributions that work in the direction of the coupling and which are the contributions that supports the decoupling. The number you can see here is the net. Okay, so the positive, the negative minus the positive parameters. Conclusions. So you can see that decomposition and decoupling analysis are generally simple tools. Simple mainly from the mathematical point of view. The mathematical procedure is simple. These are algebraic equations that we can easily calculate. From the example I have shown, we can see that the dynamics are complex. Okay, the dynamics to analyze are complex, but with the simple tools, we can go very much in detail of these complex dynamics. What I would suggest for future application is to try to apply such a kind of tool to analyze the Armenian or Caucasian context. Because the tool is valid in general, it's not country or location dependent. And so, since there are not so many analyses on the Caucasian area and on Armenia, it could be very interesting to enrich the comprehension of this area and the corresponding literature by developing such a kind of analysis. So, thank you very much for your time, for listening me. Here you have my contact, my LinkedIn page, link to my LinkedIn page, and to Scopus, where you can find The paper I highlighted you and other papers using this methodology that I mean you can use how to say to increase your knowledge if you want to gain more knowledge. But I invite you to make a literature search because there are many papers using this approach, and also industrial reports are starting to include the decomposition analysis in their studies. Thank you very much for the attention. So if you have questions, just ask.
Thank you very much, Vincenzo, for the enlightening talk on this technique that is quite useful. I'm going to ask the floor if there are any question. You know, if people have any question, we can, you know, start, you know, asking. Anyone has any question? Otherwise, I have a question.
Hi,
oh,
everyone.
Alba, yes.
Hi, everyone. Well, first of all, thank you very much, Vincenzo, for the presentation. It was very nice and something I didn't know about. So my question, it is, or maybe, I don't know, it's a thought that comes to my mind in terms of how would be this applied, like, for example, the Kaya identity or the Tapio methodology that you mentioned. This could be applied somehow to decompose the CO2 emissions, to take into account as well maybe the impact of the artificial intelligence. I think this would be something really nice to have a look now that it's gonna...
Yes. Yes, thank you for the questions. Very interesting. Yes, it's possible. Probably it's not possible now. It can be possible in a couple of years because we need the data. We need some data to, for example, related to energy consumption due to artificial intelligence utilization, I don't know, to run the server and so on. In case we have this data, absolutely the framework can be applied and can be developed. The framework is very general. So within, for example, the energy consumption of a country, we can identify the impact of artificial intelligence energy consumption, or we can decompose artificial intelligence consumption. I mean, which are the drivers that determine the artificial intelligence energy consumption. I don't know, increasing GDP, population, literacy of the population, number of people living in urban areas, and so on. Because the energy consumption will be different, you know, in the different countries, and we can see which are the parameters that can impact the energy consumption or carbon emission from artificial intelligence utilization. Definitely. The problem is to have data about this consumption or emissions.
Yeah, thank you very much. But I was meaning like the rise of the data centers. It could be countable already, because it's kind of, you have to collect the data and so on. But like, for example, in United States, they are planning to make a lot of expansion on that. So this is something that it should be worth considering in terms of studying the CO2 emissions for a country. I know that this is focused on, it's not focused on the United States, but yeah, I think...
but we can make in United States too. It's no problem. There are different studies applying the methodology to the United States. Let me say, provide that you have data about energy consumption due to artificial intelligence or carbon emissions due to artificial intelligence in the US, in Europe, or wherever you want, yes, we can perform the analysis. I mean, if you have monthly data, for example, because yearly data, I doubt that there are available monthly yearly data, we can develop the analysis monthly. It's a very up-to-date topic, so it would be interesting. In case you find this data, let me know, because I'm very interested in exploring this.
No, because I'm planning a paper on that, you know, and I was thinking about how to do it like last weeks, but I didn't know the methodology. So now that you expose the methodology, I kind of connected everything, and it would be very interesting.
Okay, let's discuss then.
Okay, thank you.
We have other two questions. Thank you very much, Alba and Vincenzo, for your answer. Alan, please go ahead.
Hi, thank you very much, Vincenzo. Very rigorous methodology, but as I said, it's very easy maybe to export this. Your presentation is very much about methodology, but does the methodology take into account like shocks to the system? And is it refined enough to capture, for instance, the 2020 war in Ukraine? Suddenly Europe starts decarbonizing much faster. That basically you capture that in the data, right? That you receive, or is there a factor too?
No, you can integrate these. I didn't show, I mean, for time limitations, but you can apply the methodology in in a chain linked base. That means year over year, so 1 year against the other. And if you do so, you can immediately see the spike, for example, caused by the reduction in energy consumption or in natural gas consumption that you have, due to the Ukrainian war. If we find an indicator, and I think we can, of the how to say the risk, let me say, that the war could happen. For example, there are indexes about the political reliability of countries. We can find a way to include this factor in the analysis, and so we can try to determine exactly how much of the consumption, of the reduction in the consumption was due to the war, and how much was due to other factors. We can try to isolate just the effect of the war. It's possible. You need to work about that. I don't have an immediate answer, but yes, it's possible to make. I need to think about which parameters can be included to represent this effect and then to quantify it.
Perfect.
Because I think for the next few decades, we might be facing lots of shocks to various systems. So I think our tools, yeah. Thanks.
Yeah. Thank you, Alan, for the question. Shahid?
Hi, Fabiano. Thanks,
Hi.
Professor Bianco, for the nice presentation. I think the idea of decomposition and decoupling is very nice. My question is related to the Kaya equation. Is it really an equation? It seems something like a mathematical expression rather than an equation if you look to the representation of the Kaya.
Yeah, it's an identity. It's an identity that is generated by using the technique called index decomposition analysis. So you split the term in a product of different indexes in order to try to understand which are the drivers that originated that quantities. Then you raised an important.
Yeah,
Please.
that's a decomposition part of the emission. But the representation seems something like equation, but in actual it is not. It is expression.
It's an identity. It's an identity.
Yeah.
Where you simply represent the carbon emissions as a product of driving forces that determines the emissions. Why? Because if you look at the raw data, I mean, you have the real data of the emission, but you don't understand why you have these emissions, which are the factors provoking the emissions, or which are the factors reducing the emissions. So that's why if you change the representation, the mathematical representation of the emissions, you can highlight which are the causes, I would say, of the emissions.
Yeah, I agree with you. Okay. Thank you.
Thank you. You're welcome.
Thank you, Shahid. Let's move on. We have other two questions. Norai, did I pronounce your name well?
Nice.
Yes, perfectly. Vincenzo, thank you for the talk. Nice to see you again. I have two questions actually. So this approach was basically decoupling GDP with carbon emissions. Can an approach like this also be used, for example, to analyze the decoupling between an economic output, let's say the GDP again, with resource use? For example,
Sure.
how much resource
Sure.
was used?
Sure.
Yes.
Definitely. I used the carbon emissions, but you can use water, you can use energy, you can use whatever you need. The methodology is general. Then you can apply, you can use tourism flow, for example. It's a general. Methodology is rather general. To resources is very interesting. It is done. If you have a look to the literature, I'm sure you will find something. I found a paper about water, but you can find also about, I don't know, critical raw materials or, you know, iron extraction, whatever you can apply.
And my second question, it relates to if somebody wants to scale down, let's say, instead of looking at it at country level, scaling it down to a smaller, more manageable, like an organization, etc. Are there approaches? I'm not sure. I don't know if this would work for an organization. Are there other approaches that you're familiar with?
Well, organization like a company, something like that, I have never seen any kind of application. If you want to scale down in terms of in territorial terms, I don't know, to a region, yes, you can make it. You can make also a geographical decomposition, so you can consider the decomposition in region. So you have a country and you decompose you analyze the contribution of each region to the country. So you can make this kind of things. To an organization, I have never seen. I cannot exclude that it can be applied, but I have never done it. I would need to think about it. Other methodologies to assess the carbon footprint of organizations and so on, yes, you have in the literature different approaches that can be used for the energy consumption, the carbon footprint, and so on. I mean, you can make for process also, but for process you would use something a bit different, more engineering-oriented approach like exergy analysis, these kind of things. But we should we can try to understand if it can be somehow applied to an organization. I mean, in principle, we can also do, because these are the parameters you decompose. We need to find the parameters. I mean, in the chi identity, if we refer to the straightforward chi identity, we have parameters that are usually calculated to countries. We need to find proxies for organization. For example, population cannot be the population, but could be the employees. GDP cannot be the GDP, but the revenues, for example. Energy consumption of the organization is the energy consumption of the organization. I mean, we can try. I mean, mathematically, it's simple. If you have the data of the organization and you can find these proxies, yes, we may do it. We may try to do it. It's a good idea, actually.
Perfect. I think we are in a very good timing. Is 55 minutes. Are there any other questions? We can close down the seminar here. Okay. I really would like to thank you, Professor Bianco, for this seminar. I really would like to thank you, all of you, to be participating to this seminar and all the questions that we had. It was quite an interesting. Let's see if in the future we will have some other development for this technique that we can do some interesting things. Today we had a couple of nice hints from, from the audience. And we think that it could be useful to apply also some part of this technique also to Armenia context and other region, not only Europe. Thank you very much. Thank you to all, and I'm going to close you the seminar. We would like to remember that the next seminar of the series will be in 1 month, and we will give you some further detail in the coming weeks. Okay? Thank you to all, and thank you, Professor Vincenzo.
Thank you, everybody.
Thank you.
Thank you, Vincenzo.
See you soon.
Bye.
Bye bye.
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 Thank
Thank
you.
you.
Bye.
Bye bye.
Bye.